talk about my, the way I try to talk about Arizona climate and thinking about climate change as somebody who's not from Arizona. I'm from Michigan originally, but I've been here for 20 years. And studying meteorology and climatology, working here for 20 years has caused me to really pay more attention to some of the unique aspects of Arizona, which I think are important for us to try to understand how it is changing and may change into the future, given how projections work. And we'll kind of go through some of these pieces and parts. And it starts here at thinking about what are the main controls on Arizona climate. And they are the very unique elements that make this place so interesting and beautiful and diverse. They're related to the types of variability that we have spatially, temporally, and over years, sort of the natural pulses of the climate system. And then how those natural pulses are actually changing and being sort of tweaked and morphed over time. And so they start off with this idea of thinking about topoclimate and seasonality. So thinking about having mountain ranges right around town, sort of wrapping around town, give us amazing biodiversity and diversity in climates as well. So watching the climate, watching rainfall this summer has been really interesting because the top of Mount Lemons had about 25 inches, but just down the hill at the base of the mountain in the foothills, there's a couple of stations that have had 15 inches of rain. So just over 5 miles and down about 6, 7, 8,000 feet, there's a 10-inch gradient, and often that's even much greater. So in the wintertime, it's not uncommon for the top to get 30 and the foothills to get maybe 5. And so just these amazing gradients that can emerge become really challenging to try to anticipate how they'll change in the future. And even just kind of paying attention to them right now is quite interesting. So topoclimate and then the seasonality of precipitation, thinking about the monsoon differently than the wintertime season. So the pulse of when precipitation comes and what it means to the environment, what it means to resource management, what it means to a lot of our resources is really different. This monsoon is fantastic, but it does very little for solving any water issues across the Southwest. And I've been getting that question quite a bit lately. Is the drought over? Well, Lake Mead is not filling up much at all at this point. And many of the other reservoirs probably won't respond much to this precipitation. We have wonderful flows in a lot of these rivers, and some of them that do have reservoirs might come up a little bit, but most of this is going to be moving around, maybe reaching groundwater in some select locations, but largely just kind of beautiful and helping the ecosystems on the short term. El Nino Southern Oscillation, we'll talk a little bit about that. That's the pulse in the winter, that we go from years where we have La Nina events like last winter. La Ninas, we know, as we anticipate a La Nina and it forms in the fall, tends to bring dry conditions and drought conditions to Arizona. And then El Ninos, when we see those coming up, they tend to kind of bring us into wetter periods in the wintertime. They don't tend to impact the summer much at all, so we don't see that variability. So we get these sort of periods over time of wetter winters, drier winters, wetter winters, drier winters, and we see that in the climate record, even going back in the paleo record as well. And then there's climate change on top of that. And its most clear expression down here in the Southwest is through temperature. And it's just this sort of creeping crud, and we'll look at some of that data. And when we have heat waves, which are kind of the normal part of the climate system, they're just a bit higher now than they would have been in the past. And so we can push past old records and thresholds more easily. It's also shifting the water balance. We're seeing less snow and more rain. The reservoir system in the Western US is built to manage snowpack. It's not built to manage rain. And that's why we're having so much short-term trouble, again, over allocation of the water system, and a lot of water policy that's been kind of antiquated and hasn't really kept up. But then that shift from snow to rain is also important in here. And then increasing evapotranspiration, we'll talk a little bit about that. That's the discussion about the idea when you hear mega drought. Mega drought is really actually talking about increasing aridity rather than any big changes in precipitation. Okay, so we'll start off with just a couple maps to orient everybody, and I want to kind of point out this idea of topoclimate. And so this is a long-term average temperature map for Arizona, created from gridded data from stations, and then we just interpolate that or statistically adjust that to elevation. So this is really an elevation map. An elevation can represent temperature when it's scaled in this manner. So higher elevations are cooler, we know that, and lower elevations are warmer. So Yuma, very, very warm climate, and Flagstaff, a very cool climate. And so just thinking about that diversity, just related to topography in Arizona, gives us amazingly diverse climates. And these gray outlines are watersheds. And so you can see the watersheds reaching up into the high areas and then getting traced down into low areas. That ends up you having surplus water because of the water balance. There's more precip, lower evapotranspiration at higher elevations can generate water, and it flows down into the drier areas. And that's a lot of our water management here in the Southwest, is just sort of taking these watersheds and using the water that accumulates at the top and then moves down in the lower areas that have deficits. Precipitation, more interesting for sure. It is related to elevation, but not completely. And we have patterns across the state. The Mogollon Rim there, which is that band of blues, dark blues, from Flagstaff over into east central Arizona, highest elevation, generates a lot of its weather because it forces up air from storm systems moving across and creates precipitation. And then as air descends on the other side of it, and if you've driven out of Flagstaff towards Winslow, you know that it goes downhill very quickly and then dries out very quickly. And so the Colorado Plateau is really a high cool desert because of a kind of a weak rain shadow that occurs from the topography of the Mogollon Rim. And then our sky islands all pop up there. They're all sticking out in the southeast part of the state as being sort of wet islands, and that is indeed the case. And that's even more related to their relationship with the monsoon season. So them sticking up into that moist air, generating and collecting all that sun can generate convection, get more rain typically on these mountains, and in the valleys slightly drier. But even the valleys in Southeast Arizona can have enhanced precipitation because of our proximity to the monsoon system. So you go further to the northwest, it gets drier because that becomes more dominated by winter precipitation, less by summer precipitation. So we see that in that elevation map again, a little more finely detailed, giving you that sense of that topographic variability. Precipitation again is just mirrored on the bottom left. And the upper right, though, I think is really interesting too, because if you look at biome maps for anywhere out east, they're very expansive and they encompass large areas because there isn't that topographic variability. You can have small things sort of oriented around watersheds and water bodies out east, but here that elevation gradients can bring up topographic and biological diversity in sharp gradients. We know that if you took a drive up to Mount Lemmon today, you're going to go from desert scrub all the way up to a conifer forest. And the other thing I want to kind of point out on this too, which I think is just really quite fascinating, is the diversity of low deserts we have here as well. So the Mojave Desert up in the northwest part of the state reaches all the way into California. So that's the Mojave Desert kind of spills into northwest Arizona. Then the Sonoran Desert is in central and southern Arizona. And then the far southeast has the Chihuahuan Desert. And so those deserts, one of their primary differences is the seasonality of the rainfall. And so the Mojave Desert is primarily part of the Mediterranean climate, which is winter precipitation only. The Sonoran Desert has the overlap of winter and summer precipitation. And then the Chihuahuan Desert in far southeast, which reaches down into Mexico, is primarily summer. So it becomes more monsoonal. And so just that seasonality of precipitation crossing over in Arizona gives us that biological diversity, is having plants and animals that rely on different seasonality of precipitation, or relying on or being adapted to try to use either. So having a winter drought or a summer drought, they can swap out and use water from other time periods. And that's also why this past year was really quite devastating drought-wise, is that the summer rainfall didn't show up last year. And then we had a dry winter, which put us into really kind of unprecedented drought conditions at least in the contemporary record. And just because we really do look at some kind of trading and swapping from between winter and summer. And so now we're in this crazy catch-up mode of record wet conditions now in this particular summer. Okay, and so just to put a little finer point on this idea of seasonality, this particular plot, I generated from this website that I like to use, and I'll just walk you through it just to give you a sense of what I'm trying to illustrate from this. So I'm taking the entire state of Arizona. We're taking all that graded climate data and we're boiling it down into basically one value for every month in the historical record. And then what we're going to do is we're going to organize each of those monthly values from the historical record. This would be monthly data going back to 1900. And then we're going to organize it along the y-axis, which is up the left side of the graph here. And it goes across from October to September. So it's organized in what we call the water year. And the water year is October 1st through September 30th. And it just organizes the year around the seasonality of precip just better. And the black line is what we call the median. Close, you could kind of think of it as an average from statistics, but the median is going to be that middle value in all of the wet to dry Octobers in that far left part of the graph. And we can trace that black line across the year to get a sense of, is it a wet month or a dry month in the annual cycle? And so October, you can see there, again, statewide average. So this number isn't particularly meaningful for any one location, but October is fairly high. It drops down a little bit in November. And then we have this kind of plateau, December, January, February, and then March, kind of similar. And then we start to drop off into April. We're drying out seasonally. This is the climatology of the seasonality here, April, May, June. So we bottom out in June. June is our driest month. And then we have this large jump up in precipitation, July, August, September, and then we go through the year again. And so hopefully it gives you a little sense of that we've got these distinct periods in the year where we expect precipitation, we don't expect precipitation in the spring, and then we move back into the summer. So this is that kind of natural pulse of changing the types of weather that we see across the Southwest. So in the wintertime, winter storm season, the weather's coming off the Pacific, out of the Northwest or off the Southern California coast from west to east, low pressure systems, sometimes cold, sometimes high elevation snow, sometimes a low elevation snow if it's a really cold system, really different, unique character of precipitation. So we get into the spring, that storm track lifts north towards the poles, and we get into, and it's replaced by high pressure, which is going to be sunny, warm conditions. It gets very hot. The sun is very high in June. And then what will happen then is that that high pressure system starts to introduce moisture from the south and the southeast, which is the monsoon. We're seeing that right now. And then what will happen through this month into next month, the sun will start to get lower in the sky. We'll lose that energy. The high pressure will sink back to the south, and then it will be replaced again by that winter storm season as we move into October and November again. So we kind of do this as we move winter type storms, reliably dry spring, back into monsoon, and then we do it over again. And all of these seasons are really quite unique. You don't see this kind of shift from what we call mid-latitude weather, which is weather systems off coming from the west to the east, to then turning into basically we're in a tropical climate right now. If it doesn't feel tropical, it very much is. So this is a tropical climate, and then we'll switch back over to a mid-latitude climate. So we're at a really unique spot in the planet to see this kind of variability over the year. All right, and so if we look across the state here, just to give you a little sense of this seasonality too, these little black bars, these are, we call climate divisions, just they're basically multi-county areas where we average all the climate data together across the state. And the black bars represent the long-term monthly precipitation. And so the first black bar in any of these graphs is January ending through December. So there'll be 12 black bars. And so it just gives you a relative sense of the long-term average precipitation signature. These would be called them climographs. So they're little thumbprints of the climate of a particular region across the state. And just to draw your attention to it, the southeast part of the state has pretty pronounced tall bars and then short bars in between, and our tallest bars are in the summertime. So that is giving you a little bit of indication is that we're more close to the Chihuahuan Desert, which is a little bit of a lean towards more summer precipitation. The central part of the state is a little bit more even between winter and summer and lower because it's lower elevation. Mogollon Rim has taller bars in both seasons, winter and summer, and then the far northwest has a little bit more of that evening as well. So just giving a sense across the whole state, the dominance of summer versus winter precipitation changes a little bit. And the reason I do all this in a climate change presentation is that projections of changes in annual precipitation don't tell us a lot because they're a mixed signal of winter versus summer. And so what we really want to know is summer precipitation going to change, and is winter precipitation going to change? And we have different answers for both of those seasons and in different certainty. So it puts the precip future kind of unclear, but we do know it's going to get warmer. So it's then trying to wrangle all of that, those ideas together and anticipating what the future might look like. Okay, and so then the El Nino Sun Oscillation I mentioned earlier is a big part of our interannual variability. We've seen that, for the last 10,000 years in the Southwest. So you can look at the deep paleo records here, and especially in the last 1,000 years when we look at tree ring record reconstructions for the Southwest, is that the big signal from year to year in winter precipitation is whether or not we're in a La Nina event or in an El Nino event. And it's part of these are the different phases of the El Nino Southern Oscillation. And what that is it's a change in sea surface temperature patterns across the equatorial Pacific from the coast of South America all the way into the West Pacific. And so we look at that entire band along the equator, and we look at the temperature patterns, the sea surface temperature patterns, and that gives us an indication as they reorganize and get cooler and warmer in different spots. That affects the weather pattern across the Northern Hemisphere and the Southern Hemisphere. In the Northern Hemisphere, in the wintertime, this left map gives us an indication that it causes a wave pattern and the storm track to shift typically north across the Pacific Northwest. La Nina winters are typically very wet for the Pacific Northwest, and they typically dry for us. We see fewer storms while they see more. And then El Nino, it's kind of the opposite, basically having the storm track park across Southern California, across the Southwest, and then even across the Southern Gulf states, steering those storms more regularly through the winter season across that band tends to enhance precipitation across all of that area. And some of our wettest winters in Arizona history are related to El Nino conditions. So you can imagine then trying to understand how El Nino Southern Oscillation changes in the future with climate change is really, really important for us. It's really important for California, it's important for the Southwest, it's important for the Gulf states. Climate models have struggled for decades now on doing a good job with ENSO. And even now with this new report, which is a synthesis of previous studies, there isn't a great consensus on how ENSO might change. So again, that's leading to some of the uncertainty that we see on the precipitation side of projections. Okay. So what I want to do now is I want to show you changes. I want to show you some of the variability that we see in the records across Arizona, and we'll zoom in a little bit more closely on Tucson here as well. So this is a tree ring reconstruction of wintertime precipitation. So that's what tree rings are most sensitive to. So if you core a ponderosa pine tree and you look at all the ring widths there, what those ring widths are going to represent is how much water that tree took up in the spring, which is in relation to how much precipitation fell during the winter time. You can scale these ring widths back to actual precipitation observations, which is called a reconstruction. And so this graph here is a November through April reconstruction. So it's an estimate of precipitation going back from 1000 AD. This particular time series ends at 1988. It's an old time series. And it's scaled to 100 means it's the average of that whole time period. And then 200% of average would be twice the long-term average. 50 would be half the long-term average. So you can see there that there's a lot of just squiggles up and down around the average. So lots of variability around the average every year. Very few years kind of hug the average. So we have lots of interannual precipitation variability in the wintertime, just kind of naturally. And then you might see some sort of groups of years that hang above 100, groups of years that hang below 100, and so on and so forth. We call that decadal variability. And so there'll be decades where more of the winters are wet, some decades where more of the winters are dry. And those longer term, that's actually where the term megadrought came from. Megadrought is a term from the paleoclimate literature, and it was basically a way of trying to show long-term persistent droughts that were decades long in the historical paleo record. So you can see here that there's a couple of longer term droughts and there's a couple of longer term wet periods. And in this particular graph in the contemporary record, there's that giant kind of jump up at the end of the record. And so this tree ring reconstruction ends in the 1980s, which were, so you can see here, one of the wettest periods in the whole last 1,000 years in this reconstruction. And it was also a period where Arizona had a lot of growth. So I think that there's a little bit of sort of a false expectation for the 80s as being normal. And it was not normal in the historical record. The 80s were extremely wet, and those kinds of wet conditions occur very infrequently. So we have more long-term droughts in our back pocket than we do long-term wet periods. And so that's another sort of adjusting your expectations for this region. And I think we're kind of waking up to that right now, especially with a lot of the water crises, because I think we had unreasonable expectations for how wet and how much water could be regularly delivered, because we have lots of variability over time. And then warming temperatures is absolutely changed that dynamic as well, making it even less efficient when we do have wet periods and less snow and generating runoff and water into the reservoirs. Okay, and so then now we're going to zoom in. This is the instrumental record. This is the record that I work with in most of my research. And so this is rain gauge estimates across Arizona, same way I was doing with that gridded data again. So we're cookie cutting out of it all of Arizona, and we're boiling it down into one number for each year for Arizona going back to 1900, right? So each of these bars is the average precipitation for Arizona, January through December from 1900, and this ends December of 2020. So it doesn't have the last 8 months in it because I didn't have the full calendar year for this year. We'll look at some more recent data into context in just a moment here, but just to give you a sense here of what have we been experiencing in Arizona in the sort of last 120 years. The orange line is a moving average, and it's centered. It's a 10-year moving average with the last 5 years and the next 5 years kind of moving along. So it gives you a little more sense of what I'm talking about is that decadal variability. So you can see there that that orange line is hanging above in the 1900s, kind of drifts down, is below average in the 1950s. That's a big drought period for Arizona in the historical record. You can see lots of kind of archival information about how that drought impacted Arizona. There's the 80s wet period that popped up again. And then you can see since the 1980s, and you can see about since 1990, more of those green bars are below the black line, which is the long-term average. And so that's our more recent drought. So it's got this, again, very imperfect, and the timing of these long-term wet periods and dry periods is not sinusoidal or regular. So it's not predictable. We just know that they occur. And so we know there are wet periods, we know there are dry periods. They're typically, the research really points to the El Nino Southern Oscillation, phases of El Nino and La Nina as being the primary determinant of these wet periods and dry periods. And there's just hundreds of papers on this that talk about connecting ENSO to this kind of variability across the Southwest. And so it's even kind of interesting here too. If you notice, since the 90s, it was down and it kind of bottomed out in 2002. And since then, there was actually a couple of years where it kind of ticked up, and then 2020 happened and it kind of cratered down again. But we're kind of at this really indistinct period right now where maybe the climate system is shifting towards the wetter period, or maybe it's just a blip in a longer term drought. And that's the real challenge, is that our climate modeling and forecasting can't really tell us anything about the next 10 years. We just look backwards and know that these longer term droughts end and we do move into wetter periods. That's still the expectation here, but we're going to do so under warm conditions. What that means for the effect of water in the system isn't super clear. And that's actually a lot of the discussion around mega drought, is that it's, even if we get wetter, it's going to be under warmer conditions. So we're still going to have water issues into the future. Okay, so we can rescale this just to pop out the longer term wet periods and dry periods. This is scaled to what we call a drought index at this point. So 0 would be near average. So if your bar is really close or doesn't exist, it's at 0, which would be the long-term average. It's a blue bar that stands way up. It's a very wet year. It's a red bar sticking way down. It's a very dry year. So you can look across there and actually see the deepest red bar was in 1956. So Arizona. So that was the record dry calendar year for Arizona. 2020 almost beat it, but didn't quite. It was actually drier in 56, which is kind of interesting. And you can see the 80s wet period there and our more recent drought, and even where that black line was starting to hug back up to zero, but it's not clear if this is in kind of a temporary thing or if we are indeed trending back towards wetter conditions. The flip side here is we look at temperature. Temperature has not had decadal variability in it. There's a little bit associated with wet periods are typically cooler, dry periods are typically warmer, but we've kind of overridden that relationship because you now see like the 80s weren't quite as cool as previous wet periods because the trend is sort of pushing on top of that. And on this, 2020 was the warmest on record, and that's consistent in a lot of other data sets. Okay, so if we take, and this is some of the stuff that I've been working on, and I'm really quite interested in because we don't have a real good our head around this aspect as much as under warming conditions, things like atmospheric demand, variables like atmospheric demand, physical mechanisms like evapotranspiration. So that's as the atmosphere gets warmer, it can not only hold more water, but it has the ability to take more water out of the systems on the ground. So it shifts the water balance. It's more thirsty, basically. And you can, it's like having a hand dryer in a bathroom. What does a hand dryer do? It heats up the air and blows that air across your hands, and you can feel your hand get cool. That's because it's evaporating water. So a warmer atmosphere is able to have the ability to hold more water vapor in the atmosphere. So if we think about warming temperatures and we think about precipitation, there's going to be more atmospheric demand. So this Drought Index is taking temperature trends and precipitation variability and sort of pushing them together. And we can see from this is that the 50s drought, which was cooler because we didn't have as much temperature trend back then, is not quite as bad as the more recent drought. The more recent drought is warmer, but it's not even quite as dry as the 50s. So basically what it is, it's flipping drought on its head and saying, well, it can rain whatever you want as far as long-term variability, but under warmer conditions, it's going to create more intense drought conditions. So we've got a communication issue on science with this because drought is a term that is supposed to describe temporary anomalies in the climate systems. Droughts should end by definition, otherwise they're not droughts. And that's what we're talking about now, is that as warming conditions occur, you're really talking about a shifting baseline and the place is getting drier and more arid. So it's a better way of thinking about this particular observed shift, is that we have increasing aridity now with increasing temperatures. And we need to think about that because the water in the system and the effective water in the system is shifting. And you're going to see things change based on increasing aridity, like what plants can grow where, how much water we would expect to see in natural systems, and how much water we have to manage in reservoirs and such. Okay, and this kind of shows up in some of these maps. And so these are, so many red maps in the media and on TV over the last year because it's been such a deep drought situation. And so the map at the left was the 12-month period ending in December. So that had both last summer's dry conditions and the beginning of the winter, the very dry fall and winter of 2020. So red on the map, on that upper left map, means deep drought conditions, very rare conditions in the historical record, if not record. The map at the right is the temperature record. And so all the dark red means it was the record warmest January through December, ending in 2020, of the whole historical record. So record dry, record warm, put those together, you get unprecedented drought levels based on increasing VT. And so that's what we saw with this other drought index at the end of 2020, right? And so now we're in this really kind of interesting period. Now we have record wet conditions. We're now trying to assess, like, well, how effective is all of this rain all at once in the summertime going to be at solving drought problems? We're not sure. I mean, it's going to help, and it's clearly helping a lot of desert adapted plants. Trees can't take up water this fast to solve a 20-year deficit. And then a lot of this water isn't making it anywhere near the groundwater systems because it can't, it's disconnected. and the reservoir systems don't really respond to summer precipitation, even when it's very wet. So, this is great, but it doesn't necessarily solve all of our sort of accumulating longer term problems. Okay, so this is kind of that punchline again that I think is really important to hold on to, and we're trying to figure out how things are changing and will change here in Tucson and the broader Southwest here. Is warming temperatures can shift the average soil water balance. And so increasing temperatures lead to increasing potential evapotranspiration, which is really synonymous with increasing aridity. And so these are kind of these terms here. Potential evapotranspiration is warmer, drier conditions, more atmospheric demand. So there's more potential to take water out of the atmosphere, which is synonymous with increasing aridity. And again, this is on average over time. And so very wet conditions like right now are wonderful and great, but we're really kind of looking at the sort of 10-year moving window. And things like big reservoirs, natural springs, trees, anything that integrates climate over long periods of time tell a better story about the slowly shifting part, even if we're going to get wet and dry extremes through that. So thinking about this on average over time is really important. So knowing that it's getting warmer, precip needs to increase to meet increasing potential evapotranspiration for the water balance to stay the same, right? And so on average over time, getting regular amounts of precipitation to meet that atmospheric demand was part of the natural climate system. But as it gets warmer, to meet that water balance, it needs to rain more, right? And so for us to see no big shifts in ecosystems and climate down here, as it gets warmer, it needs to rain more. And none of the projections necessarily say that that's going to happen. We could see more variability, which could lead to more deeper droughts in between as it's warmer, maybe catch up events like this. But as I mentioned before, we don't really have any way of storing 12 inches of water in 4 weeks in any meaningful way. And it's also interesting, kind of on a side, water harvesting, very, very old technology, really wonderful, serious thing we should think more about at scale here in the Southwest. And you even see that even, some city projects, trying to figure out how to capture stormwater and infiltrate it and being able to use it for other irrigation purposes. Okay, and then also the kind of precip matters, snow versus rain, when and how much and how often. So really keeping track of when these events are occurring and how much, and the spacing of them to try to meet this water balance need over time. Okay, I'm going to skip that one. Okay, I'm sorry, this one it's got a lot of information. I'm going to walk you through it real quick, and it's rough on a Saturday morning, but this is one of the sort of technical graphics that I try to use to keep track of precipitation variability at different times. And so just real quickly, and if it doesn't make sense, I can come back to it. But what it is it's basically tracking climate variability at the monthly scale for Arizona in that bottom graph. So those green bars sticking up are wet months, unusually wet months. Brown bars are sticking down. And this drought index is windowed. And so what we can do is we can look at just the particular month. Is a particular month very wet or very dry relative to the historical record, which would be at the bottom of this heat map at the top here. And so it'll be green or brown based on what it's doing the month. But what's more interesting is to try to move that window out. So if we look at the last 6 months and move that along, is it wet or dry, the whole 6-month period? Is the whole year, 12 months, wet or dry? Is the last 5 years wet or dry? And that's where you start to see these kind of colors open up. And we can see both short-term and long-term droughts emerge in this. And so just to kind of orient you is that you can see the 80s wet period opening up those big, long green. It was just a long periods of wet conditions. About 2002, we opened up these longer, slower moving windows of dry conditions. The green starts to show back up again, as I mentioned, kind of 2013, 2015. It was one of that last big El Nino event in 2015, 2016, kind of pushed us a little bit towards the wet side. More recent drought really kind of clobbered us. The last strip on the far right of the graph there is July 2021. And so it's got all time periods from July 2021, the 1 month, to the 2 month. And so it grows up to being the last 60 months or 5 years at the top of the graph. So we can look backwards from July 2020. What I think is really interesting with this graph is it has right now, and this is such an interesting characteristic of Arizona drought, we have basically very wet, lack of short-term drought conditions. But if you look at the last 12 to 18 months, we have deep drought conditions. Because when we lump in last winter and last summer, we have not met the deficits that have accumulated there. But at the very short-term window, it's very wet. So that's kind of this thing of trying to articulate like great wet conditions in the last 4 weeks. But when we're thinking about slower varying climate, we have not even come close to solving or filling back up the bucket that was left empty by missing the summer and winter precip. And we get this kind of phasing at all different timescales over time. So just again, you know, I get this question a lot: is the drought over? It's not over. The longer term drought takes many seasons, because it accumulated over many seasons, to actually get us out of it. So next winter's wet, next summer and next winter are all average to above average. We can start talking about a real reversal in that longer term drought that we're in. But again, right now, wonderful, but has not solved long-term problems. Okay.
Mike, we're at,
good, Stuart.
We're at 10:40 now, which was our original thought. Is this a good place for break, or would you like a few more minutes to reach out?
No, this is great. Yeah, do you want to take a quick break?
Well, the idea was it's 2.5 hours, and I think the mind can absorb only as much as the seat can endure.
That's right.
So
that's right.
How about if we take a 10-minute break and start crisply again at 10:50?
Sounds great.
Okay, so everyone, I'm going to turn off the recording. I forgot to mention to you, we are recording this. If that's a problem, I should have asked before. Please let me know in chat. We will, I'll put on a little music. I will disappear because I can't turn off the video without an erroneous picture showing up. And we'll start again at 10:50. Great stuff.
Good.
We're looking forward to it.
Okay. Okay, welcome back, everybody, and let's jump right into. So this kind of phase of the presentation will kind of wrap up looking forward now, and I'm going to do just a couple of quick slides on the 101 climate change, and I'm sure this is just review for everybody, but I think it's just kind of helpful to kind of touch on these concepts again. And it comes down to the IPCC report is 4,000 pages long, but it all stems back to this fundamental understanding we have of the role of greenhouse gases and how they change the energy balance of the whole system. And it really comes down to, I think, this rather cute animation of a carbon dioxide molecule and the ability of greenhouse gases, carbon dioxide, others, methane, nitrous oxide, or other greenhouse gases, but their ability to basically have solar radiation, which is high energy and at short wavelengths, penetrate the atmosphere. And as the sun's energy strikes the surface, if it goes through and is not reflected back to space, if it strikes a dark surface, that dark surface absorbs that solar energy and basically converts it into thermal energy. Thermal energy is at much longer wavelengths. So there's a shift in the type of energy, wavelength-wise, from short, high energy solar radiation into basically thermal energy, which is long wave radiation. And so a dark asphalt parking lot in the summer is a perfect experiment. The sun's beating down, strikes the surface, it absorbs that energy, converts it to the thermal energy, and then starts to radiate it back out as heat. And that long wave radiation, as it goes up and tries to go back out to space, greenhouse gases are actually opaque to that kind of radiation. And so they're not bothered by solar radiation coming in, but they are bothered by long wave radiation trying to leave back to space. And so as that long wave radiation tries to go back to space, molecules in the atmosphere absorb that energy and then start to radiate it out in every direction. And part of that is radiating it back down. So basically it slows the ability of this long wave radiation to go back out to space. And that's kind of it. And it gets more and more complicated as you try to think about water vapor, which is a greenhouse gas. More of it's in the atmosphere as it gets warmer, but then clouds are at different levels and it gets more complicated. But this fundamental changing of the energy balance because of greenhouse gases is it. And then everything stems from this fact. And we look at long-term, this is actually from an old IPCC report, is tracking temperature change over the last 1,000 years for the globe, CO2 concentrations, and then carbon emissions are all tracking up at the same time. And so they're all connected and related to each other, as the shift in the chemistry of the atmosphere is causing a shift in the energy balance over time as well. And this is from a more recent National Climate Change Assessment report. This was actually in 2017. Same kind of graphics we've had for a long time. They just get updated a little bit more. The top graph is long-term variability of like hundreds of thousands of years. It's CO2 amounts. The middle one is methane. The bottom is nitrous oxide. The graphs on the right are the more contemporary from 1750 past the year 2000. So just looking at those more recent trends. The graphs on the left are reconstructed from ice core samples. So you can drill down an ice core and look back hundreds of thousands of years with actual real samples of gas that was trapped in the ice. And then more recently, we've got ways of measuring the changes here. And you can see really unprecedented shifts in not only carbon dioxide, but also methane and nitrous oxide. And since the basically industrial revolution and a lot of industrialization that's occurred over the last couple of decades. And then we see temperature rising in concert with carbon dioxide concentrations. This would be correlation. Correlation is not causation. So how do we actually get at understanding that greenhouse gases are indeed causing these changes in temperature? Climate science is not it's not a field experimental science. It's not like science in a benchtop in a lab. It's not like field trials that you do out in sort of ecological studies. We have to do most of our attribution with climate modeling. And so climate modeling will work where we build a mathematical model of the climate system as best we can, try to get all of the parts and pieces in the physics right. And then one of the things we can do is we can run it backwards. And so we can start in the deep past where we've got historical observations and then run it forward and then compare it to our observed record to see how well it emulates what actually happened. And then we can also change parts of the model to enhance the greenhouse gases or take them out completely to see if that particular switch in the model causes any changes in the model's behavior. And so this is from one of the early IPCC reports, is showing here that the observed record is the black line. And then the modeling is if we only have natural variability, just volcanoes erupting occasionally, and then the 11-year solar cycle, which indeed does influence climate, is the blue modeling exercise. And then the red one is those forcings as well as adding greenhouse gases and sulfates. So both not only things that enhance warming, but sulfates can actually reduce warming because they reflect some of that sunlight back out to space. So you can see here that the only modeling runs that replicate the increase in temperatures are having the greenhouse gases in the model. So that's an attribution exercise. And there are more and more about that, is how do we know things are changing? It's through these modeling exercises. And I just saw this figure. It was new to me. It was in one of the more recent, it was 2018 anyways, 3 years ago, National Climate Assessment Report. And this is actually from an old figure from Jim Hansen from in the early 2000s. We've continued to use it. And I think it's really handy and it'll probably useful. You want to give you the slides, you can look at this particular figure. It's got the link there, a little more description on it, but it basically partitions out all of the different talking points we have around, well, what is causing what? And so the top there is the black line is just we looked at as the observed temperature trend, but then we can look at the natural drivers. And so if the natural driver is above zero, it's contributing to warming. If the natural driver is below zero, it's contributing to cooling. So that yellow line is all natural drivers. And then you can see here that volcanoes, solar variability, and then orbital changes are very, very small. So all the natural drivers are very small relative to the changes we're seeing here. The middle one is all human influences. So greenhouse gases is that purple line above the black line. So it's suggesting that it's actually contributing more warming than is even being observed. And that means that there are other things that are tugging it back down. So changes in ozone, changes in land cover, and changes in aerosol have actually tugged down the impact of greenhouse gases over time. And so then the bottom panel is all drivers with observed. That's attribution. So we not only look at natural variability, we also look at these other anthropogenic influences, put them all together, it's still net positive towards warming. Okay, so then we're going to finally wrap up here with looking at some of the climate projections going forward. And one of the things, I just got this question this week, which was there was interest in knowing what the climate outlook would be for the next 10 years. And it is the hardest, it's basically impossible to actually anticipate what the climate will look like in the next 10 years. And this comes out of a report, one of the other national climate assessment that just shows us where we're at with modeling. And at short timescales, internal variability of the natural climate system rules. It's what it dominates the whole, everything that we see here. And those would be things like El Nino and La Nina. There are other oscillations across the planet. If you lived on the East Coast, you'd know about the North Atlantic Oscillation. There's discussion about something called the Arctic Oscillation, which can create, that's the polar vortex. When we hear about the polar vortex encompassing the Eastern US, that's related to the Arctic Oscillation. We have shorter term and longer term variability. So all of this kind of reorganization of energy that's going on is dominant at short timescales. As you get further out, though, when we use climate models, the scenarios become more important. I'll talk about that. And scenarios are, how do we anticipate the level of greenhouse gases in the atmosphere changing into the future? Do we expect to see a technological breakthrough in fusion and greenhouse gas removal takes off, or we don't have any technology breakthroughs and coal all of a sudden becomes more important in 20 years? That's the kind, those are the scenarios that become the bigger part of the uncertainty, but greenhouse gas forcing changes later in the record give us most of the variability across the outcomes. Okay, and so there are some great articles on possible futures. If you're into like trying to understand how greenhouse gases might change in the future, this link I have down here on the right is a deep dive by one of the IPCC authors, and he wrote this this article in Nature that I have clipped out here. And basically, it's when you look at an IPCC report, you've got these things that used to be called, I can't remember what they were called. They were called relative concentration pathways. They were like RCPs. They're now called SSPs. And so they're different than RCPs from the past. Anyways, you go way deep on it. The point of this is when you look at climate projections, you're going to get choices on futures to see how those futures might play out with local climate conditions. And so we've got worst case scenarios, which are this high 5 degrees C change. And if you've heard about a lot of the discussions in the news, we're trying to keep it at 1.5 degree change. 5 degrees would be crazy change. And what we're seeing now with commitments, technology, and this is from the International Energy Agency, looking at plausible paths forward, given even just how much coal is available given the market right now, puts some of these worst case scenarios actually very, very unlikely. So highly unlikely. 4 degrees C warming is unlikely. So we're kind of in this now 1.5, 2.5 to 3, which are still really big changes for the planet, but it's kind of narrowed our future. And it gives us a way of looking at climate projections, I think, a little bit more responsibly. Fortunately, most of the climate projections you're going to find out there on the web are going to be this 8.5, which is probably not even possible now, and something that's kind of down in the middle here. So hopefully in the next couple of years, we're going to see more climate projections using these other kind of constrained scenarios. But right now we don't have a lot of those available to us. So what I'm going to do is I'm going to show you this tool. It's been around for years now, and it needs to catch up with some of the new projections, called the Climate Toolbox. Very, very usable. And what you can do is you can drop a pin at it and look at the previous era climate projections in local climate units. And so these are summer temperature projections. And I draw your attention to the top here because it has lower emission scenario RCP 4.5. And so would be a good outcome. We should be lower than this, hopefully, but it's kind of in the middle. So this is kind of a middle of likely outcomes right now, based on our understanding of scenarios. And so it still shows a bit of change, right? So there's the 90s, 2025, which this is interesting because we're almost to some of the future projection periods. So we'll actually be able to check our math and check our work on this. But you can see here is that it gets warmer, and that's just clearly what we would expect here. And it's a shift of about 5 degrees on average by end of century. And these are Fahrenheit now. We're talking about Celsius and a lot of these other discussions. And the bottom is actually 8.5. So this is an unlikely outcome unless something really goes off the rail as far as policy, or we have some unknown feedback that we haven't kind of constrained well in future modeling, like something else pops up and releases a bunch of carbon to the atmosphere, or there's other things we don't know. So it's not completely off the table, but it's highly unlikely at this point. And it's a big shift by end of century. The climate of Tucson is much closer to Yuma than it is Tucson that we know. So we can look at this in comparing these two different emission scenarios. And again, remember that the red line is the higher emission scenario, which is unlikely at this point, and the lower is kind of probably middle. So the scenarios kind of span this kind of blue area right here. So again, it's warming through the annual average out into end of century, just as we would expect. Precipitation, though, to just kind of bring it back to what we've been talking about earlier, is large. So that that gray area around that black line, the black line is the average. And so you can see over time is that we don't have trend in precipitation because we just have longer term cycles. And if you average those longer term cycles, they average out to zero. It means there's droughts and wet periods in there. And that gray area is the range of variability within all of those cycles. And then in the future, you can see there's not really any net change. It doesn't point down as far as precipitation. The areas around that model uncertainty actually grow. So that could be a suggestion of increasing variability, increasing extremes, hovering around basically the same mean amount of precipitation. But again, remember, warmer conditions increase aridity. So even under that same precipitation variability, we have less effective precipitation and water to deal with. So the same thing, just splitting it out by season, winter up at the top there, it's got this real subtle downward slope. And that is possible in the climate models, is that the storm track lifts slightly north of us over time. And so we might have a drying signal in the wintertime. It's much more pronounced in the spring. The summer, really no net change. And that's because our ability to model the monsoon isn't very good. Doesn't mean the monsoon won't change in the future. We just don't have a good sense of how it might. And it may just be the same, but more kind of extremes as far as heavier precipitation, maybe more breaks the monsoon. Not sure at this point. Okay, and then finally, it's starting to trickle out now, but these modeling efforts are tied to the Intergovernmental Panel on Climate Change reports. So the last IPCC report came out a number of years ago, had its own modeling effort, which was called CMIP-5. So this new report has CMIP-6. And so I just showed you the last generation of climate model output. The new generation of climate model output is now out, but it doesn't have all the nice, fancy, cool tools that make it usable. I did find one tool that allowed us to kind of look at precipitation projections for the Southwest, given this new CMIP modeling projections here. And it's kind of interesting. It's not hugely different from what we've seen in the past. And so this left upper panel here is potential changes in winter precipitation. It's kind of interesting. You can see California actually getting wetter, and Arizona's at this break point where the southern part of the region might get drier, and right through there is no change. And so we've seen this kind of come out in literature. And again, we're not clear. It could be that there's some kind of enhancement of precipitation across the Pacific that is now showing up in these new models. the summertime, this is really interesting to me here, which is it's showing kind of wetter conditions with the summertime going forward with this particular scenario. So we still have a lot of work to do to try to sort out how precipitation is going to change. Temperature, though, it's kind of the same. And inland locations tend to warm more. It's just like we're seeing with the summer. As you get further south, you get more into more oceanic effects. And in the summertime, the same thing is that much of the warming is actually north of us and more inland areas, which we've even seen kind of this summer as well. Okay, skip that because that's kind of in there as well. And so just to close it out, and we'll have some time for questions here. So we have complex hydroclimatic variability at weather timescales dominate all of Arizona. So like what we've seen last night, later in July, these kind of cycles and periods of weather contribute most of our annual total, and they come in really interesting packets of weather throughout the year. And that leads to high levels of interannual variability. And so climate models, they project similar, if not higher variability in the future, as I showed you the kind of that range of that envelope. And the precip projections, again, have much higher uncertainty. We still have work to do to try to figure that out. But we know temperatures are expected to warm dramatically in the century under the high emission scenario. So it's still totally within, and I think we really are getting our act together on sort of wrangling in. You can see even the scenarios are starting to take out the high emission ones and really kind of push us into a tighter envelope of possibilities. So totally possible for us to wrangle the temperatures in and not see some of these, kind of extreme outcomes at end of century here. In the interim, though, the temps are going to continue to warm until we really plateau and get emissions leveled and then go in the opposite direction. And so given that, we're going to have warmer temperatures, and that in its own right will increase aridity and continues to change the water discussion here in Arizona, which is something we certainly will have to keep track of. So I'll leave it at that, and I'm happy to field some questions before you move on to your next section today.
Thank you, Mike. I invite everyone to simply unmute and ask a question, or if you'd rather type a question. Okay, Rocky, why don't you start us off?
Yeah, I have tons of questions, so I'll try to be quick. So my first question was the graph that had all the warming projections paired with policy that said 5 degrees was unlikely, and then it was but it was incorrectly labeled as business as usual.
Yeah.
Why is that? You said it was impossible. Why is it not impossible, and why is it wrong to say that that's business as usual?
So I really invite you to check out the link there to kind of do a deep dive on that. Okay, so the business as usual approach is old terminology, and the policy shifts that have occurred, since this kind of term was first brought online. The business as usual at this point doesn't have the fossil fuel portfolio in it that it used to, right? And so you can look at some of these papers now, and the shift in energy policy has made it that coal is way more expensive to extract than the market will allow. And so you'd actually have to have reversal of a bunch of economic factors that would make it likely to have that much extraction at this point. And it happens subtly and kind of in the background over the last decade. Coal was, even without the market signals and the push towards renewables, it wasn't a great energy source. And so it's now made it much more difficult internationally to even keep it as a viable energy source, which I thought was really interesting. I hadn't realized that was going on in the background.
Mike, Nancy asked, oh, sorry, you want to have another one, Rocky?
Yeah, is that okay?
Go ahead.
Okay. You said that we were close to being able to check our math at that 2025 point. If the math is wrong because we mitigated and stopped emitting so much, do you have ways to recalculate and say oh, okay, our math was right, but we fixed it. We fixed our output. So, this is the new projection.
Yep, absolutely. And so there's some efforts that actually do climate model tracking. Every year they'll look at a suite of models and they'll look at what was observed. And I can point you to that. So there's a great, I totally forgot the website off the top of my head. But anyways, there's some posting where they'll revisit, and then they'll say, and the models themselves work really, really well. They just need to be fed the right scenario. And, you know, there's all of these scenarios. There's only one actual thing that happens. And so the scenarios are trying to actually follow all of these little subtle shifts around. And that's where the IPCC reports, they are slow processes, and these scenarios end up taking a year to bake, and then they run the models, and then it takes like 4 years to generate the report. But at the same time, tons of things have happened, and so the scenarios may or may not quite reflect what's actually happened on the ground. So our process isn't quite as nimble as the changes that are occurring, but there is that recalculation that is happening on a yearly basis.
I can let someone else go if someone else has questions. I have like two more kind of quick questions.
Tell you what, let's take Nancy's and then circle back to you, Rocky. Nancy asked, Nancy, I'll say this unless you'd like to jump in.
Yeah, no, I can join. I'm just wondering if the climate models are projecting the increased carbon from the quickening of the melting ice in the Arctic. And I saw some documentary about the decomposition of the boreal forests, how once that starts happening, that could really throw a wrench into everything.
Yeah, so there are carbon cycle feedbacks that are part of the model. And right now they're constrained to being the best guess at this point. And they do have things like temperature feedbacks with permafrost melting and release of methane, and carbon cycle changes in decomposition associated with like boreal forest changes and even wildfires. And so it is all in there. But again, this modeling is sort of constrained towards our best understanding. And it doesn't mean that there couldn't be some, surprise that shows up. Like we didn't quite understand how permafrost melting worked at the methane release and those kinds of things. But it could also be that it could go either way, right? Like it could be that the model is too bullish on it or not bullish enough. And so that does leave some of the, and that's why you see us always talk about likely, highly unlikely, it doesn't leave out the possibility of any of these other things going, because, the science is happening in real time. It doesn't even, it's learning while it's observing, which is kind of the fundamental part of this whole thing. Is like, it's not a great way to run a society when you're experimenting on it at the same time, right? And so that's why trying to rein it in is much better in the longer term, just from being prudent as a species.
Thank you.
Mm-hmm.
Okay. Rocky, why don't you go ahead?
Awesome. So another thing that you mentioned was the miscommunication about what drought means. And I know that a lot of these models that you showed were like hard to understand for some people. Do you have any tips on explaining difficult models to people, or is there another thing we should focus on when talking to people about fixing the climate?
Oh, it's such a good question. Yeah. Yeah, the modeling is, it's not the thing that I focus on either, right? I mean, the modeling is a, well, it should do two things. And the first thing it should do, and this is really what modeling is for, is to try to understand how a system responds to some kind of change, right? I mean, and that's really what climate modeling is for, is like, if you change greenhouse gases, do we get the system to change in this way? And that to me has always been enough information to say, okay, we probably don't want to do that, so we should put some policy around it. But the way that we work as a society, we also want to predict and plan. So then we really try to push the models to tell us, okay, so how much warmer will it get if we do this particular thing, right? And that's where I think we get a lot of kind of noisy conversations about, like, well, is it right? And, well, it wasn't right with this, so why should we trust it with any of those kinds of things? The thing is that we roll back the basic fundamental science of how the physics and thermodynamics work. We know, like, that's provable. You can do a home experiment to show that. And it's like focusing on that, to me, seems more useful than getting in an argument about whether models are right or not, because they're not. Again, it's like there's this old quote by George Box, which is, all models are wrong, some are useful, right? And that's just a truism. I mean, that's just what it is that they're not going to be right to the level that I think people want them to be, but that doesn't even matter because we have enough knowledge right now to know, you know what, we should really wrangle some of this stuff in because it leads to greater uncertainty in the future, which, like in our society, like businesses hate uncertainty. So it's goofy that we even get into territory where you'd have something uncertain like this to have to try to plan around.
Awesome. And then I have one more question. I also don't remember if I thanked you for your time, but thank you so much. This was a really
yeah,
awesome
absolutely. No, this
conversation.
is so cool. You guys are, this is so awesome. You're spending your Saturday morning doing this. I really thank you all.
Yeah. So your job is really hard because you have to look at kind of depressing data all the time. How do you keep yourself from becoming discouraged and continue moving forward?
Yeah, that's a good question. I have this disposition. I'm just kind of a hopeful person. I'm not delusional or denialist by any means, but I'm still I'm delighted by the science and studying the weather and the climate, and that keeps me sane. And just the small bits of action that I can do kind of within my own life keep me engaged on the issue, and then knowing that there are people like you who are spending their time doing this, and there's just so many hopeful signs out there that I really believe, rounding the corner on this, right? And so I don't think we need to be hopeless at any in any way at this point. I think that we need to be realistic about the idea that we're going to continue to need to adapt to some hopefully small changes because we'll get it sort of under control, and realistic about those things, but that we really are kind of coming together on this. So I'm just and I don't even think it's naive, but I'm hopeful on this.
Awesome. Thank you so much. Those are my
Yeah, absolutely. Thanks, Rocky.
Yeah, thank you, Mike. I've got a question. We had a lot of rain.
Mm-hmm.
You said that this amount right now would not really be enough to do much more than to take the load off our what we're pulling out of the aquifer from our irrigation systems and making everything happy. So can structures such as Sabino Dam be modified to slow the release of water into the valley so we can attenuate the benefit? And then a corollary to that is, you mentioned rainwater harvesting, and I guess you can call stormwater management as a bigger concept. What designs do you think would be most useful for us as citizens, or maybe more important for the city to be working on?
Yeah, this is I'm an enthusiast in this area. I'm not an expert. And so I'm a little bit on my lane, but I'll just kind of give you my thought. And there's some really good folks at U of A who thought about this. And it's interesting because I've seen this from two different perspectives. I work with a colleague who works for USDA, Department of Agriculture, who works with ranchers actually on implementing check dams. And so when you've got large landscapes, one of the things that you'll do to try, and what can happen in degraded areas, out in rangelands with heavy rains, is that you can have, large storms come through, and then you get channels that will cut arroyos. And so you just have movements of sand. And so one of the strategies is to put small check dams that, as you point out, Stuart, slow the water down and cause infiltration. And what it does is it actually stores the soil moisture in deeper and deeper. And then you can have revegetation that'll occur, right? And so that's an old practice. And there's some policy issues that make it illegal actually to do check dams based on DWR policy, and I think even EPA policy. So you can't impound waters of the United States. And so we have some policy things to work out to get climate adaptation really back up to speed, because there's old things, and it's even like water harvesting. Water harvesting in some communities is illegal because it holds back runoff that belongs to some other utility, right? This happens in Colorado, and I think it was even an issue in parts of Arizona with Salt River Project. And so we've got to, and that makes home rainwater harvesting not possible. And there's another research group on campus that's been looking at green infrastructure, and they've done some really cool stuff on studying curb cuts. So taking water in streets that would get quickly moved out to like the middle of Tucson Avenue and flooded out until I got that storm grate. But to then you've seen them around town, right? So there's the little curb cuts with the trees that then causes trees to help grow, and that causes shade. And if they're mesquite, they even have other resources associated with them. So there's that kind of stuff I think is really clever, rather than the old stormwater mentality. And I used to work in stormwater long time ago, which is the engineering approach, which is you try to get water as fast out of cities as possible. And we're now rethinking that, like, well, hold up, maybe we can put it in retention ponds, and maybe we can get it to actually infiltrate to some kind of mechanism that would be allowed to make it to groundwater. That's really hard because it's so deep, or be used for other purposes. And this crunch we're in with water is really bringing out all of those clever ideas and making them like, oh yeah, that's a good thing to kind of drag back into the present.
Can you tell us the names of those individuals that you mentioned are working on?
Yeah, so I don't know if any of you know Tom Meixner. He's a hydrologist. And
he'll be speaking to us.
Just have him go off on this, because he knows a ton about this, and he led a big NSF project that studied this, with water quality, water yields, and a bunch of modeling. So it'd be really interesting to get his take on this.
Great. So they finally got the grant. That's great news.
They did. Yeah, they had one, and then I think they've got another couple, because they've been really successful in packaging it and having great results out of it.
Thank you. Now, there was another question. Tori just commented that with Water Management Group, they did some work like you were talking about.
Yep. Water Management Group, I think, was associated with some of those projects, and Water Management Group's been doing those practices anyways. I think Tom's group just came along and helped quantify, some of the impacts that those projects were having.
Super. Well, let's see if there's any more questions. Just unmute if you'd like.
Can we find out about your Wrangler Award?
Yeah, I'll tell you the quick 1 minute version. I had a project with some colleagues here at the University of Arizona, some range scientists, and we worked with the Forest Service and the Gila County cattle growers on drought planning in Gila County. And they have a bad history. There's a lot of conflict between the Forest Service and the ranching groups up there, just because of collisions over forest management and particular drought. And so we got a project together where we kind of helped mediate between these two groups, and then did a study to try to help them collaboratively figure out how to do drought planning together and improve communication so that they were better prepared for the next drought. And we had some evidence that it worked and it was helpful. And so they were appreciative and gave us that that Chamber of Commerce award, we had a nice dinner out of that with them. So that was really cool.
Mike, do you have either a write-up of that and or a way to teach others how to take that approach?
We do. So and again, it was a team project with social scientists. So it was an interdisciplinary team. So we knew how to work at it from both sort of the physical science and the information and data side, to having the facilitation and the being able to sort of study the human dimension side of that. And I'll try to think about if I've got a little write-up on that I could share with you.
I'll tell you, Bonnie Colby, you might know. So
I know Bonnie well. Yeah.
Great. Well, she's very much into this kind of collaborative work, and she'll do a session with us as well. So
that's so good.
I think we're all interested in how do we meet in a place where we all can do something together versus argue or avoid or deny.
Totally agree. And the only way we're going to move forward on this is recognizing that we're all in this together, regardless of our, any of our stripes that we're wearing.
Wow. Okay, last call on question or comment.
I have a question. I was looking at your different scenarios, and I agree with you. We're not going to do business as usual. Things are getting better across the country, and other countries are taking it more seriously. And I see that in the state where I came from, Illinois, where a lot of coal plants have been retired because they can't compete anymore. They're too expensive to operate, so they're going down pretty quickly. It's a question of what they're going to be replaced with: natural gas, solar plus batteries. But I wanted to, in your scenario where we meet the Paris targets, and I think that's oh, thanks for pulling that back up.
Yeah.
Are we going to have to rely on pulling carbon out of the atmosphere under that scenario, or is that something where we may move to more of a worst case sort of, or average no policy worst case sort of scenario? Because I see some organizations, scientists saying we may have missed the boat, and we may have to rely upon technologies that pull CO2 out of the atmosphere in the future.
Yeah, this is a good question. And again, I'm more of an interested citizen on this side of it. And again, like, I really recommend this article because it goes into some of the uncertainty and whether or not what kind of suite of technologies are employed in some of those. Some of the, like, I think that the 1.5 down here, that mitigation has a lot of technology in it, and some of it is unproven. And
okay.
my guess is that probably in the 1.5, and again, I don't totally know, but I think this article that I shared with you has a little more detail on that, does start to employ carbon removal technology, which has been really, I've read countless sort of news articles on that because I'm really quite fascinated if it's like a boondoggle or if it's a real thing. And it's got like really high level, like Cal Poly and MIT and, billions of dollars in there. And I can't tell if it's like a fancy version of snake oil or if it's like a real thing, but it seems like it keeps getting the investment. And so there's some signaling that it's a real thing. The scaling of it seems crazy, like to get it to scale to actually make a difference. But some people continue to think that that's actually going to be something in the future. And I've been completely fascinated with all the cold fusion stuff too, which is the same thing. I can't tell if it's a thing or it's not a thing, but it's being written about as a thing. But so those are two like technology things that if they actually worked and scaled would make a lot of other challenges like really go away. So I think the more realistic is that those are probably still sci-fi and could be helpful, and that there's still all the real work of scaling proven, reliable technology up. And I don't know if anybody's listened to Saul Griffiths on so there's this wonderful series of podcasts by Ezra Klein on Vox that he did a couple years ago, and his series of climate activists and scientists talk about it, and it's one of the best sort of series of thoughtful people. But Saul Griffiths is a physicist, and he got a MacArthur Genius Award, but he wrote two books actually, called Electrify Everything, and it's just such an interesting, his take on what's the solution orientation we need to be in right now to actually move fossil fuels off. And it's super daunting, but he's got it all laid out. He's like, if we do this, we do this. He even got me to think about my hot water heater is at its end of life. And he says, if you're there, switch it over to an electric heat pump. And so he got me thinking like, okay, I'm going to do this because I think this is the next thing. Like, this is an action I can take at home. is proven reliable technology, moving to electric are kind of the on the table things that we should be focused on right now.
Mike, that's exciting. And Danya, I think, has a question. I want to pass something to Jessica first, though, because you've talked about some of these ancient technologies, such as check dams, other rainwater harvesting approaches. And Jessica, what about, are you going to touch upon, when you present to us in a few weeks, will you touch on the carbon sequestration potential of soil? I'm not saying you should, but I'm just wondering, will you?
Yes, always.
Ah, great.
Yeah, I plan on talking about that. I was trying to formulate some good questions about it, but I didn't really come up with anything that was tangible. So I don't know if Michael has anything to say about soil and carbon sequestration.
Yeah, I again, it's way out of my lane. I have in my department, we've got a couple of soil carbon experts. Joey Blankenship is a new faculty member in our department in the last couple of years, and he's really fantastic. So it could be another person you could try to connect with if you want a deeper dive. And he's been doing some experiments right now on soil carbon sequestration through different kind of ag practices and natural revegetation projects as well.
What was his name again?
Joey Blankenship. And he's in the Department of Environmental Science with me.
Thank you, Mike. That's a great referral. Danye.
Thanks, Stuart. Michael, first I wanted to ask you if you wouldn't mind just putting the name of that series and the author of the book in the chat.
Yep.
I would love to come back to that. And I just wanted to mention that Project Drawdown is really interesting, to think about this topic as well, because all of those are technologies that already exist.
Yep, that's such a good project. Yep.
And that was it. Thank you so much.
Thank you.
Okay, so I think we are going to formally shift focus, but not really. Oh, Nancy, did you have something still?
I just wondered if we can get a copy of the presentation.
Oh, absolutely. How, Stuart, can I just send it to you?
That's the easiest way, Mike.
Okay.
I will post it. Apparently there's a way to post a PDF on Google Docs, and someone will let me know if it doesn't work. So I'll send you a note about that. And speaking of just little businessy things.
Yeah. Thank you, Michael. This is wonderful.